In this video, I'd like to talk about the structure and properties of carboxylic acids, and one of the main properties we're going to be interested in is the acidity. So like aldehydes and ketones, we have a carbonyl carbon that is going to be sp2 hybridized, and it has a trigonal planar geometry. Unlike aldehydes and ketones, carboxylic acids are capable of powerful hydrogen bonding because we have a hydrogen directly connected to an oxygen. And this includes intermolecular hydrogen bonding within molecules of the carboxylic acid. This gives it much stronger intermolecular forces than most of the other compounds that we've considered, even relative to alcohols that are also capable of hydrogen bonding. If we consider acetic acid, or the more full name would be ethanoic acid, and compare it to its alcohol counterpart ethanol, you can see that due to the much stronger hydrogen bonding in the carboxylic acid, we have a significantly higher boiling point than we do even then in an alcohol. So carboxylic acids are weak acids, and when reacted with a base, they will donate a proton to that base, in which case they're converted to a carboxylate ion. The sodium here is just a counter ion, so oftentimes what we're really interested in is, rather than the whole carboxylate salt, really just the carboxylate ion. When we're naming carboxylate ions, they'll have exactly the same name as the parent carboxylic acid that it came from. We'll just change the ending. Rather than oic acid, it becomes oate. So in this case, benzoic acid becomes the benzoate ion. If we're naming it along with a sodium, then the whole compound would be sodium benzoate. But again, this sodium is largely a counterion. It's very often the carboxylate ion that we're interested in. Now, being weak acids, when they're in water, carboxylic acids only dissociate slightly. So when I just add it to water, most of the molecules remain with the hydrogen attached. Only a very small percentage dissociate when dissolved in water. The pKa of most carboxylic acids is between 4 and 5. We have a couple examples down here of benzoic acid, acetic acid or ethanoic acid, and propanoic acid here. So how do carboxylic acids compare to other compounds that we're familiar with? Well, the very strong inorganic acids, HCl and H2SO4, are much, much stronger than carboxylic acids. These compounds dissociate almost completely in water, being strong acids. However, compared to alcohols, carboxylic acids are quite acidic. So compared to many other organic compounds we've studied, these carboxylic acids are fairly acidic. We have a pKa difference between a typical alcohol and a typical carboxylic acid of more than 10. That means the carboxylic acids are 10 orders of magnitude stronger. So we're talking about something that's on the order of 10 to 100 billion times stronger acid than an alcohol. And the reason for this strength of acidity, at least compared to, say, alcohols, is due to the stability of the conjugate base. Remember from last semester, we talked about the stability of conjugate bases. We used ARIO. Oxygen, being fairly electronegative, is quite good for stability, but even more important in this case is the resonance. It's the resonance stability of the carboxylate ion, making it relatively stable, therefore its conjugate acid being relatively strong. Now, I mentioned that when we take a carboxylic acid, assuming it's soluble in water, and we try to dissolve it in water, it only dissociates a very small amount, and the vast majority stays together with the hydrogen attached to the rest of the molecule. It stays together as HA. It doesn't dissociate into H plus and A minus. But if we change the pH, this can have a significant effect on the extent to which carboxylic acids dissociate, and whether it exists primarily as the acid form or as the conjugate base. And remember from Chem 1212, when we have an acid in its conjugate base, so when we have the acid form and the carboxylate ion together in significant concentrations in the same solution, it will act as a buffer. It will resist changes to pH. And the way we calculated the pH of buffers was using the Henderson-Hasselbalch equation. And so this also tells us something about the ratio of the amount of conjugate base present relative to the amount of the compound that exists in the acidic form present at any given pH. And so if we compare the pH to the pKa of the acid, it will tell us what form the compound is going to exist in. When the pH is much less than the pKa, it exists almost entirely in the form of the acid. When the pH is much larger than the pKa, it exists almost entirely as the conjugate base. And when the pH is relatively close to the pKa, and we're talking within a unit, so if the pKa was 4.5, if the pKa was 4.5, we would say a close pH is something on the order between 3.5 and 5.5. In that region, we have significant amounts of both the acid and its conjugate base present at the same time. The last thing I want to consider is the effect of substituents on the acidity of carboxylic acids. And this is largely going to be dictated by the induction effects when we think about the stability of conjugate bases. Remember, we have atom size, resonance, induction, and orbitals. So another way we can influence how acidic these carboxylic acids are on how stable we can make the conjugate bases, or the carboxyl ions, by induction effects. So if we notice, the more chlorines I put onto this carboxylic acid, the more acidic it becomes. And the effects can be significant. We can go from a pKa of 4.8 to a pKa of 0.9, almost 4 pH units, or 4 orders of magnitude. We're talking 10,000 times change in the acidity by adding these chlorines. And also remember, the closer the electron withdrawing groups are to the negative charge, the greater their effects. So in this case, we can get the pKa to drop more by having the chlorine closer to the resulting carboxyl ion than when it's further away. We can also see these effects on benzoic acid. Here we have a number of substituents all in the pair position and how they affect the pKa of benzoic acid. So just regular benzoic acid would be here with a pKa of 4.2. Chlorine is mildly electron withdrawing, as we learned last chapter. That reduces the pKa a little bit. Methoxy group would be moderately electron withdrawing. That has a somewhat larger effect. A nitro group is strongly electron withdrawing. That has an even more profound effect. Whereas in the other direction, an alkyl group is moderately electron donating. That actually increases the pKa. And then we have OH, which is strongly electron donating. That increases the pKa, making it less acidic.